Good morning, students. In this section, we will discuss about reflection coefficient. Reflection coefficient K, and it is one of the very important topic in transmission lines. Before starting to reflection coefficient, we have to know about two definitions, two important points. That is incident wave and reflected wave. First one is incident wave and reflected wave. Incident wave and reflected wave. These are the 2 points you have to know. And first thing, incident wave. Simply, it is defined as, incident wave is defined as a wave which flows from sending end to the receiving end with decreasing amplitude is called as incident wave. Simply, incident wave is nothing but a wave which flows from sending end to the receiving end with decreasing amplitude is called as incident wave. That means, for example, using it is a sending end, SENDING, sending end, and it is the receiving end. Incident wave is nothing but a wave that will be starts at this point and travels and reaches to the incident wave. During this journey, the amplitude of this wave is reduced. And similarly, reflected wave is nothing but it is also sending wave, sending end. It is the receiving end. That is the receiving end. Now, a wave which flows from receiving end towards the sending end, from this point to this point with decreasing amplitude, that is called as reflected wave. That means like this. When a wave travels in this direction, that means reflection end to the sending end, that is called as reflected wave. Sending end to the receiving end is called as incident wave. These are the 2 points you have to know before starting to our reflection coefficient. Now, reflection coefficient K. Reflection coefficient K. It is defined as the ratio of amplitudes of reflected voltage or current to the incident voltage or current. That is simply the reflection coefficient K is defined as the ratio of amplitudes of reflected voltage or current to the incident voltage or current. That is the ratio of amplitudes of reflected voltage to the incident voltage or reflected current to the incident current. That is the formula for reflection coefficient K. That is K is equal to reflected voltage at load divided by incident voltage at load. That is, it can be represented as, that means it is the formula, it can be represented as reflected voltage, that is VR, reflected voltage by incident voltage, that means forward voltage. It is the forward voltage and it is the reverse voltage. Forward voltage, reverse voltage, VR by VF. Or in terms of current, it can be written as minus IR by IF. Minus IR by IF. It is the formula for reflection coefficient. Now we have to derive the expression for reflection coefficient. That is expression for reflection coefficient. Expression for reflection coefficient. To find the expression for reflection coefficient, let us consider it is equation number 1. Now we know that the basic transmission line equations. We know that the basic transmission line equations. We have already derived these equations in our previous sections. The basic transmission line equations are simply V equal to Vf into e power minus gamma x plus Vr into e power gamma x, and I equal to If into e power minus gamma x plus Ir into e power gamma x. Let it as equation number 2 and 3. Now consider equation 2. Consider equation 2. Here equation 2 is V equal to Vf into e power minus gamma x plus Vr into e power gamma x. Now I am making, that means apply differentiation with respect to x on both sides. I am making differentiation here for this. So by applying differentiation, here is V. So it will become dV by dx equal to simply this dV by dx equal to, at this time, Vf is arbitrary constant. So Vf into e power minus gamma x into minus gamma. Here we are making differentiation with respect to x. The multiplicand for x is minus gamma. So here it is minus gamma plus Vr into e power gamma x into gamma. Now take minus gamma as a common term from these two. That is equal to minus gamma into Vf into e power minus gamma x minus Vr into e power gamma x. Actually here we are having minus gamma, so we are letting here we are having plus gamma. So when we take here, we are taking minus into minus plus, that is dV by dx equal to. From our previous discussions, we have some value for dV by dx, that is minus I into r plus j omega L. It is the expression for dV by dx. This one is already derived in our previous sections. So substitute this value here. So minus I into r plus j omega L equal to minus gamma into Vf into e power minus gamma x minus Vr into e power gamma x. Here minus get cancelled, and I am taking this r plus j omega L to this side. Then I equal to gamma by r plus j omega L into Vf into e power minus gamma x minus Vr into e power gamma x. Now I am substituting the expression for gamma. We have already derived in our previous section for gamma. Gamma equal to square root of r plus j omega L into g plus j omega c. It is the expression for gamma. Now I am substituting this gamma here. So by substituting that value, by substituting this value here, then I equal to gamma is nothing but square root of r plus j omega l into g plus j omega c by here the term r plus j omega l is here and the rest of the term as usual into Vf into e power minus gamma x minus Vr into e power gamma x. Now here in the numerator root r plus j omega l and in the denominator r plus j omega l. When we write here square root of r plus j omega l into g plus j omega c by this one, this term I am writing as root r plus j omega l into root r plus j omega l. Then it will become r plus j omega l. Vf into e power minus gamma x minus Vr into e power gamma x. Here this one will get cancelled. Then we are having this one by this one, square root of g plus j omega c by square root of r plus j omega l. Then square root of g plus j omega c by r plus j omega l into Vf into e power minus gamma x minus Vr into e power gamma x. Now we have already expressed this term as a characteristic impedance, that is 1 by z0 into Vf into e power minus gamma x minus Vr into e power gamma x. It is I. Now I am letting this equation as 4. Equation 4. Now I am considering a small transmission line. That line already you have considered in our previous sections. Same transmission line I am considering. Consider a transmission line as shown in figure. Consider a transmission line as shown in figure. Simply that is like this. A transmission line with a load ZL. ZL is the load. It is the source end, it is the load end. And at source end the voltage is Vs. At source end the current is Is. At load end the voltage is VL, voltage across the load. Here it is Vs is voltage at source, current at source, and current at load is IL. IL is the current at load. VL is the voltage at load. Vs is the voltage at source, input voltage or source voltage. Is is the current. And I am assuming it is the X end, it is the Y end. X end, Y end. Two ends I am assuming. That means the source end is X. The load end is Y. Simply we can write from these existences X is equal to minus Y. X is equal to minus Y. It is the source end, it is the load end. So with these two, X is equal to minus Y. Minus Y I am writing. So from these existences I am writing few parameters. From the figure, here the value of X is equal to minus 5. Now I am substituting this value. At equation number 1 and 4. This is the fourth equation we have already derived right now, and these are the equation number 2 and 3 we have already derived. Now I am substituting that condition in equation number 2 and 4. So first I am writing equation 2. That means from equation 2 we have, just look at here, equation 2 is this. This is the equation 2. That is V equal to Vf into e power gamma x. So V equal to Vf into e power minus gamma x plus Vr into e power gamma x. That's I have assumed as a equation 2. I have assumed as a equation 2. So now I am substituting this condition, that is x equal to minus y in this equation. By substituting that, V equal to Vf into e power minus gamma into x is nothing but minus y plus Vr into e power gamma into minus y, because x equal to minus y. Then with this, V equal to Vf into e power gamma y plus Vr into e power minus gamma y. Let it as equation number 5. The same process has to do for equation number 4 also. Now consider equation 4. Here the equation 4 is this. This is the equation number 4. Now I am assuming that equation, that is I equal to 1 by z0 into Vf into e power minus gamma x minus Vr into e power gamma x. That is equation 4. Here also I am substituting x equal to minus y. Then I equal to 1 by z0 into Vf into e power minus gamma into minus y minus Vr into e power gamma into minus y. That equal to 1 by z0 into Vf into e power gamma y minus into minus plus minus Vr into e power minus gamma y. We are getting like this. So it is equation number 6. Now I have to analysis equation 5 and 6. Then I am getting the expression for reflection coefficient K. Now finally, from the figure again. Look at here. From the figure, at y equal to 0, that means at this end. Here the value of x is 0. Here the value of y is 0. So at y equal to 0, the value of I is IL, the value of V is VL. Again, look at here carefully. At y equal to 0, that means at this position, the value of I is IL and the value of V is VL. That's I am writing. That means at y equal to 0, from figure, at y equal to 0, I is equal to IL and V equal to VL. Now substitute these two values. These two values in equation 5 and 6. 5 and 6 we have to substitute. Now equation 5 is, equation number 5 we have already written here. V equal to Vf into e power gamma y plus Vr into e power minus gamma y. That's I am taking now. That is V equal to, from equation 5, V equal to Vf into e power gamma y plus Vr into e power minus gamma y. It is equation 5. Now in this equation 5, we have to substitute these values. We have to substitute. So look at here. Initially V is nothing but VL. Simply VL is equal to Vf. There is no substitution for Vf. So write it as it is. Vf into e power gamma y is nothing but 0 plus Vr into e power minus gamma into 0. Then Vl is equal to Vf into e power 0. Anything power 0 is nothing but 1. 1 plus Vr into 1. Then with this Vl is equal to Vf plus Vr. Vf plus Vr. And assume it is equation number 7. Assume it is equation number 7. Similarly, now equation 6. Now equation 6 is this: I equal to 1 by z naught into Vf into e power gamma y minus Vr into e power minus gamma y. Thus I am writing here from equation 6, I equal to 1 by z naught into Vf into e power gamma y minus Vr into e power minus gamma y. That is equation number 6. Again, in equation 6 I am substituting the same conditions. Here I is nothing but IL. IL is equal to 1 by z naught as it is into Vf into e power gamma into y is 0 minus Vr into e power minus gamma into 0. E power gamma again 1. So that equal to 1 by z naught into Vf into 1 minus Vr into 1. That equal to 1 by z naught into Vf minus Vr. 1 by z naught into Vf minus Vr. So finally Vf minus Vr equal to, I'm letting this z naught to this side. So IL into z naught. It is equation number 8. Equation number 8. It is equation number 7. It is equation number 8. From these two equations, now I'm doing here 7. Equation number 7 plus 8. I'm adding those two equations. Now look at here, equation 7 is Vf plus Vr. So Vf plus Vr. Equation 7. Vf plus Vr and Vf plus Vr. And equation 8 is Vf minus Vr plus Vf minus Vr equal to, those are the two LHS. And RHS here is VL. Here is VL. So VL. And here is IL Z naught plus IL Z naught. Here VR get cancelled. 2Vf equal to VL plus IL Z naught. Vf is equal to VL plus IL Z naught by 2. VL plus IL Z naught by 2. It is the expression for Vf, forward voltage. Similarly, we have to do 7 minus 8. Equation 7 minus equation number 8. 7 minus 8. Now here the 7 is this again. Vf plus Vr is equal to VL. So Vf plus Vr. And equation number 8, Vf minus Vr, minus of Vf minus Vr equal to, at LHS from 7 we are having VL. And here is IL minus Z naught, minus 7 minus 8 na, so minus IL Z naught. And with this Vf plus Vr minus Vf, minus into minus, plus Vr equal to VL minus IL Z naught. Vf get cancelled. So 2Vr equal to VL minus IL Z naught. Vr equal to VL minus IL Z naught by 2. It is the expression for VR. Now we have VF and VR. So finally we had to calculate the reflection coefficient. We have already derived, we have already defined the formula for reflection coefficient, K equal to VR by VF. So now I am letting this, that is from equation 1. From equation 1, K equal to VR by VF. From equation 1, K equal to VR by VF. Look at here, it is equation 1. K equal to VR by VF. So here the value of VR is this. Then K is equal to, VR value means this one, VL minus IL Z0 by 2 divided by VF. VF value is this, VL plus IL Z0 by 2 divided by VL plus IL Z0 by 2. These two will be get cancelled. Then we're having K is equal to VL minus IL Z0 by VL plus IL Z0. Now I am taking IL as a common term, IL from the numerator. So VL by IL. Here there is no term of IL. So within the denominator we are getting VL by IL minus IL is taken out. So the rest of the term is Z0 by same IL, VL by IL plus Z0. This IL will get cancelled. Now here, look at here, VL by IL means ZL. VL by L means ZL. Then K equal to, here also ZL. That is ZL minus Z0 by ZL plus Z0. ZL plus Z0. It is the expression for reflection coefficient. Is very important. Reflection coefficient. And the range of reflection coefficient is K is minus 1 to 1. Very, very important point. Range of reflection coefficient K is from minus 1 to 1. And the expression for reflection coefficient K is ZL minus Z0 by ZL plus Z0.